All right, today's notes we're going to look at some limit properties, kind of some ideas that we want to start leaning toward calculating limits algebraically. We've looked at them graphically, we've verbally described what a limit is and what we're talking about there, and we've looked at it numerically by looking at the table either on the calculator or by creating a table ourselves. So what we want to do is start looking at algebraic methods of calculating limits so that we don't always have to rely on a graphing calculator, our knowledge of graphs, or a table of values. We're going to start with some basic facts about limits of what we say are very nice functions. And nice functions for us are going to be continuous functions. So you'll hear me continually talk about continuity. That's one of these main themes that's going to come up in pretty much every section. We're going to talk about continuity. And this idea of the fact that if a function is continuous, we know that it has a function value. The limit exists as x approaches c, and the function value and the limit are the same. So the nice function is nice because when I want to calculate the limit, since it's the same as the function value, we will always use the function value to calculate the limit. So pretty much when you're doing algebraic limits, if you know it's continuous at x equal to c, just plug it in, and then that's all we're going to do. We call this direct substitution. Okay? So if we know a function is continuous at the point x equal to c, then we can use the function value and not worry about doing any algebra or graphs or numerical method. So for example, these first four that we have here, the limit as x approaches c of k, which is nothing more than your horizontal line. You're thinking your function is what's in this location. So we're basically looking at the graph of f of x equal to k, a horizontal line, which of course is continuous. And you know the y value for every x. When you plug in any x, you get a y value of k. So every y value, when I do the limit as x goes to c, is going to be k. The limit as x approaches c of a line, y equals x. So here I'm looking at the graph of f of x equal to x. Continuous, no problem. Just plug in your function value and get what your function value is. F of c would equal c. Here, f of c would equal k. All we're doing is direct substitution. If you have a power function where n is a positive integer, squared, cubed to the fourth power, fifth power, and so on, all odd power functions and all even power functions are continuous functions. So we would simply plug it in. Our graph would be f of x equals x to the n, and if we want to calculate the limit, we would do f of c, which would be c to the n. We're just plugging it in, as long as you know that it is continuous. Okay, over here, we'll put a little star by this one. If I had an odd roots are nice continuous functions. So if I wanted to calculate this, if I had something like f of x equals the cube root of x, then to calculate the limit as x approaches c, let's say 8, let's pick an example here, of the cube root of 8, what I know, oops, sorry, undo that, cube root of x, that if my function is cube root of x, it's continuous, I can get this limit simply by doing the cube root of 8, which happens to be 2. My answer is 2. I know where the function values are going. Now there is a caution about this one, because we talked about it being continuous. Now you have to be careful with even roots, because if you look at y equals square root of x, the square root graph, if you will remember, actually is only continuous on its domain. And it's not continuous at x equal to 0 because it doesn't have a left limit when you're looking at it. It only has a right limit and a function value. It's going to fail part 2 of your definition of continuity. So when we start looking at the limits, the limit as x approaches 0 of square root of x does not exist. Now that's why you have to be careful about direct substitution, because it only works if you know the function is continuous at that x value. Since the square root graph in any even graph is not continuous at x equal to 0, we would say that this does not exist. So you just have to be careful about that. If I was going to do the limit as x approaches 1 of square root of x, Well, that one's fine. At 1, this function is continuous. It has a function value. The left and the right limit are the same. I could simply plug it in and get my function value. So provided it's continuous at x equal to c, you can plug it in. Be very careful about plugging in when it is not continuous at that point. And that's why you got to have a good knowledge of continuities and discontinuities and where they occur. All right, so those are the basics, the nice functions. Now we're going to come in with some properties that rely on the fact that we have a limit on a function f of x, and it exists. Say we call this one m. You have a limit on a function g of x, and it exists. We'll call this n. And those functions themselves do not have to be continuous. We're just saying we have a function f, and we know the limit as x approaches c exists. Could be a point discontinuity there, could be continuous there. We don't know. What we definitely know is there's no regional discontinuity at that point. There's no infinite discontinuity. There's no oscillating discontinuity, because the only type of discontinuity where you have a limit that exists is a point discontinuity. So we don't know whether it's continuous at c or it is a point discontinuity at c, but since the limit exists, we know that we have one of those two options. All right, and here are some additional properties that you get when we start combining functions together. Suppose I took a function and I multiply it by k. That if I were to multiply a function by k, that's nothing more than a vertical scaling factor. So if I had a function, we'll just look at a continuous one. Suppose I had a cubic coming in, and I was interested as x approaches 1, which of course is continuous at x equal to 1. If I were to take this function and multiply this function f of x and change it into a function that was 2 times f of x, well, what happens? It takes each y value and doubles it. Even the ones that are next to it. It's not going to all of a sudden become some kind of a discontinuous function when you do a vertical scale. And since the limit is the y value, it becomes twice as much. That you can essentially factor out a multiplicative constant. That a vertical scale, the limit of a vertical scale times a function would be the vertical scale times the limit. Okay, so that's fairly straightforward. And that works even if it's discontinuous there. Of course, the only discontinuity that it could have is a point discontinuity. But if I had a function coming in, and this was my f of x, and then I did 2 times f of x, well, every y value gets doubled. It's still a hole in that location. But when I double all the y values, sorry, it's got to go through there and then double there, stretch them away from the x-axis, it's still going to be a point discontinuity at that point. It's not going to change what's there, so it's still going to have a limit. It doesn't have, f of x doesn't have to be continuous anymore here. It just has to have a limit when you were doing it. So scaling does not affect it. You just pull the scale out, find the limit of the function. If I'm doing the limit of the sum or difference of two functions, well, when I do the sum or difference of two functions, remember all you're doing is adding the y values. So if I add the y values of f to the y values of g, hopefully you'll see that to figure out where the y values went when I do a limit, I can take the limit of the first and add it to the limit of the second, or subtract depending on what you want to do. Up here, you would have just done k times m. That it is that simple in finding the limit. That's called the sum and difference rule. If you look over here at the next one, we have the limit of a product. Works the same way. You multiply your y values. Whether it's continuous or not, we don't care. If I have functions, suppose I have, we'll just make them really simple functions here. Suppose f of x is a constant function with a hole in it. And then suppose g of x, maybe we'll make that another one, maybe a line. And we'll make that one have a hole and be defined over here and keep going. That if I'm multiplying these two functions together, all you're doing is taking y value times y value. If this is 1 times 2, your new function would end up at 2. If this was 1 times 3, 1 times 3 would be 3. And it's still going to have a hole in that location. Your function would end up, as you multiply, not really changing the type of behavior that you have. The limit will still exist. So the limit of a product is the product of the limits. We're okay with that. So it's still pretty easy properties. Now here we just have to be careful. And what we have to be careful of is whenever the denominator is 0. Okay? If the limit on the top exists and the limit on the bottom exists, and the limit on the bottom function is not 0, then the limit of a quotient is the quotient of the limits. Now notice that this is not saying that the limit does not exist if we do have 0 in the bottom. Okay? Remember that limits exist provided we have a removable discontinuity. If we end up with the limit in the denominator being 0, but we had a form 0 over 0, which is what we call our indeterminate form, which is a clue that we may have a removable point discontinuity. So at this point, if we do have the limit as x approaches c of g of x is 0, we don't want to say that we don't have a limit or the limit doesn't exist. There's going to be, we're going to call that the do more work form. Okay? So if it works, it works. If it doesn't work, if the property doesn't apply because of this, if this is true, you're going to have to calculate the limit using another method, which means do more work. And you'll start to see in this set of notes what that do more work is going to be as we come across some of these. All right? Then we have the limit of a composition. Now this one is the one that always trips people up. And what you have to realize is that this is a two-step process. That you're not just doing direct substitution, okay? You can only do this limit of a composition, the limit as x approaches c of f of g of x is only equal to f of g of c if the composition is continuous at x equal to c. So that's the first fallacy. You guys love direct substitution so much, you're always direct substituting. That can't happen. You have to be very careful. If it is not continuous at x equal to c, you have to do a two-step process. Your two-step process is first, just like when we do composition, you got to figure out where the inside goes. So your first step in the process is to calculate the limit as x approaches c of g of x. Where did the inside function go? Once you get that, and I'm going to call it L here, so I say it exists and I found it and it's L. Once I find that, that is currently where you are. What you want to think of is that really, technically, what you're doing when you do this is the limit as x goes to g of x of f of x. That this new limit becomes the L becomes the new limit. Because you first figure out where the inside went, and then you use that to figure out where the outside goes. And it's a two-step process. Okay? And again, I can't stress this enough when we start doing examples, that in many cases, functions are nice. And remember, nice means continuous at x equal to c. And that if they are nice, then you will want to substitute, because if it's continuous, we've already learned that direct substitution works. But you have to be very, very careful about composition and continuity. Because, for example, suppose I had the limit as x approaches 5 of the square root of x minus 5. Okay? Now, I can direct substitute here all I want. I can plug 5 in, okay? So if I had my f of g of x, which is equal to square root of x minus 5, think of it that way. Your g of x is x minus 5. Your f of x is the square root of x. And hopefully some alarm bells are going off, because we know that a square root graph has a regional discontinuity and its endpoint does not have a left side. So what you want to be careful of here is recognizing that, could I direct substitute into this? Well, sure I can. That if I was going to do f of g of 5, that's perfectly fine. Square root of 5 minus 5 equals square root of 0, and you will be tempted to tell me that the limit is 0 because you've direct substituted. However, that only works if the function is continuous at 5. F of g of x is not continuous at x equal to 5. That's a square root graph that's been shifted to the right 5. So at x equal to 5, it has an endpoint. There is a regional discontinuity there. So what you're thinking about when you do this problem, the reason why we say always do a two-step process, is you first ask yourself the question, okay, what is the limit as x approaches 5 of the inside function, x minus 5? That's continuous, and I can direct substitute 5 minus 5 or 0. Once I do that, this becomes the second step. I am now doing the limit as x goes to 0 of the decomposition, pull it apart, square root of x. And then you have to remember, oh, wait a minute, that x goes to 0, that's a regional discontinuity. This is a does not exist. Okay, so I'm just cautioning you. Be very careful about direct substitution. You can only use direct substitution if you know it is continuous at x equal to c. If it is not, you have to follow the properties that we have. All right. Now, some other properties that are a direct result of the ones we've already listed. The power rule. Okay. If I have a function raised to any power, provided that we don't have a discontinuity, okay, so that's kind of this composition rule, provided the limit as x approaches c of f of x, we would find that to be L, and then provided the limit as x goes to L of x to that power of n exists, then we can do a direct substitution. So provided we know that we don't have a discontinuity here, we can go ahead and do that direct substitution and get L to the n. That's what we're basically saying here. Okay? So for example, when you have a square is easy. We know that squaring something is not going to create a discontinuity. Even if f of x has a discontinuity, if it has a limit, then we should be okay. Here's one way of doing it, kind of a long way. The limit of a square is the same as taking the limit of a product. The limit of a product we know is the product of the limits, and if this exists and that exists, then we are basically squaring the limit, that we can go from here to here. Where we want to be careful is when you have a negative exponent, because that's really a division by 0 issue that you have to look at, or when you have a fractional 1/2 because you have a regional discontinuity. It's all about continuous versus discontinuous when you are doing these problems, so be very careful on that. All right, like here's an example when you have a negative. F of x to the negative 1 really means 1 over f of x. The limit of a quotient is the quotient of the limits, which is only true when, and we can only use this limit property, this quotient of the limits, provided the limit on the bottom is not 0. Okay, the limit of a constant is the constant, and then this limit we would know, we would basically end up with, if I knew this limit was L, 1 over L. Okay, provided L is not 0. Now again, if L is 0, that doesn't necessarily mean that our limit does not exist, but it may. We would have to do more work. Okay, and then when you have the case where n is a fraction, you want to be careful of regional discontinuities. You don't want to run into that idea of, hey, I'm at the endpoint and that's going to give me a problem. What you want to make sure is that the limit as x approaches c of the inside function is not going to 0 when you have a square root function or a fourth root function or any of those, because you would be on the endpoint where you have a regional discontinuity. So those are some cautions. And a lot of these problems, it's going to look like you're going to do direct substitution, and you have to be careful. You only use direct substitution if you know you are continuous there. All right, let's take a look at some examples. So here in this first one, we have a given limit. The limit exists, it's 8. The limit for g is -2. The limit for h is 0. And we want to find the limits that exist. Okay, and if it doesn't exist, we're going to explain why. So now let's take a look at this. Here, the first thing is I have the limit of a difference. And according to our properties, that means I can do the limit as x approaches c of 2f of x minus the limit as x approaches c of 3g of x. The limit of a difference is the difference of the limits. And then we can continue this down even farther and say, well, these are scalar multiples. I can pull that out. So when I'm looking at this problem, I say scalar multiple, pull it to the front. That's 2 times the limit as x approaches c of f of x minus 3 times the limit as x approaches c of g of x. So we're down to here. Now, I don't care if when you're doing these problems you go directly from this line to that line. That's perfectly fine. You're using 2 properties. The limit of a difference is the difference of the limits, and the scalar multiple we can factor out. Once I get to here, I can simply finish the problem. It's 2 times my limit on f is 8 minus 3 times my limit on g is -2, and we get our final answer 16 plus 6 or 22. Okay, so it's a fairly straightforward process, provided we're okay on the limits and we don't end up at a discontinuity somewhere. Here we're squaring. Squares don't have any discontinuities on them, so I'm good with applying our property, our power rule. And I'm going to apply the power rule. I'm going to do it in 2 steps and then show you can skip over some. The limit of a function to a power is the limit of the inside, x approaches c, of 2g of x, and then you're simply going to square it. And then we go, okay, the limit of a scalar multiple, I can pull that out. It's 2 times the limit as x goes to c of g of x, and then that whole thing is being squared. And so now we get to here, we're ready to plug things in. The limit for g was -2, so I have 2 times -2, and then we're squaring it, so I have -4 squared, or final answer of 16. Okay. Now, taking a look at this one, we're going to do the limit as x approaches c. We have a square root, and so we got to be careful about that one, right? We want to make sure we don't get 0. I'm going to think of this as, can I split this? Well, we can split it provided the limits on the bottom are not 0. Sometimes we go ahead and we start splitting until we see what happens. So I'm going to do the limit as x goes to c of the square root of 3 plus f of x over the limit as x goes to c of x times g of x squared. Okay. Now I have the limit of a product here in the bottom. So let's work on the bottom for a little bit. The limit of a product is the product of the limits. Okay. Now, this part of the bottom, I'll come back to the top in a second. The limit as x approaches c of g of x squared, well, we've already figured out, we did some work over here that we can see that we can just square what the limit was on the inside. The limit as x approaches c of g of x, and then we can square it. Now over here we have the limit as x approaches c of x. Oh, wait a minute, that's a continuous function, it's a line. I can just plug that in. I'll get c there. Okay, and then scrolling down, obviously didn't leave us enough space here on this one, which I'll fix for next year, doesn't help you any. Here the limit as x approaches c of g of x was -2, -2 squared. And so in the bottom of our fraction, after all that work, we have 4c. Now notice I have linkage going here because I am ignoring the top for the moment, but I'm going to come back and put it in. Okay? I was just taking care of the bottom as I went to get down to my 4c. Now we come back to the top. So on the top, we have the limit as x approaches c of the inside function. Now I'm going to be very careful about that because I need to make sure it's not 0. So I might come up here on the side and say the limit as x approaches c of 3 plus f of x. We're going to figure that out first. The limit of a sum is the sum of the limits as x approaches c of 3 plus the limit as x approaches c of f of x. The limit as x approaches c of a constant is the constant, plus the limit as x approaches c of f of x was 8. So we end up with 3 plus 8, or 11. All right, so we're okay. The inside doesn't go to 0. So once I have that limit, now I'm going to do the limit as x approaches 11 of the square root of x. Right? We figured out where the inside went. That inside limit that we just found becomes the new limit on the outside function. We decompose the function, figure out where the inside goes, and then use that to figure out where the outside goes. So let's continue our process. Now we're okay because the square root function is continuous everywhere except x equal to 0 and where it's undefined. So I can now just plug in 11, square root 11, bring down square root of 11, and square root of 11. So there's my answer for that one. A little bit more complicated, but take it step by step and use the properties. Now, even if I didn't give you the limits like I did up here in example 1, here in example 2, we can use graphs to get limits. So I'm pretty much giving you the limits by giving you the graphs. So like looking in here at this little category, I might decide, okay, what I need to do here is maybe go ahead and use the graph to find the limit as x approaches 0 of f of x. And I'm going to need to find the limit as x approaches 0 of g of x, because I see that I have combinations with f and g in here as x goes to 0, and I don't have any composition or roots. I have a power rule and a scalar multiple and those kinds of things. So I'm going to come up here to my graph of f, and as x goes to 0, we're going to find that answer. The limit is 2, so I'll write that down. And then I'm going to come over here for g of x, and at x equal to 0, it's continuous there, it's going to have a limit of 0. So I find my two values. Then we're back into the same problems we had above. And we will let you shortcut a little bit. We'll say, what properties are you using? Go all the way across and say that, well, I know that I can take a scalar multiple out, and if I'm going to do the limit on the inside, then you can square it. Okay, so that would get me to there. And I can do the sum and then do the limit as x approaches c of g of x. That I am essentially breaking it down into its component parts. And then now, because I just figured these things out from the graph, I'm just plugging them in. So we would have 2 times 2 squared plus 3 times 0, 4 times 2 equals 8. And then we have our limit. So we're applying the properties. And yes, you can do more than one in a step, but be careful as you're doing these that you pay attention to some of those pitfalls that we've talked about. All right, let's take a look at the next one. I'll change color so that it's easier to see, separate it from that one. I have the limit of a quotient, and I'm going toward -3. So again, I'm going to come up here and I'm going to say I'm going to need the limit as x goes to -3 of g of x. And I'm going to need the limit as x goes to -3 of f of x. And I'm using my graph to get those. So I look at my graph. G of x is this one, -3, 1, 2, 3. The y value in the limit is 1. So this is equal to 1. The limit as x approaches -3 of f of x. Okay, so now we come over here to f of x and we go to -3, 1, 2, 3. Our limit and our function value is -1, so equals -1. So now I'm ready. I have that. I've got that from the graph. I'm ready to do my problem. All right, we start our work. The limit of a quotient is the quotient of the limits, and we can do that provided the bottom doesn't have a limit of 0, which we already figured out it's -1. All right, so we're good with that part. Limit as x approaches -3 of f of x. Now the top is the limit of a product, which is the product of the limits. Limit as x goes to -3 of x squared times the limit as x goes to -3 of g of x. Now we already figured out this part and this part using the graph. So the only thing left to do in this problem is the limit as x approaches negative 3 of x squared. X squared is a continuous nice parabola, so I can use direct substitution. Negative 3 squared for that limit. This limit, g, was 1, and the bottom limit, f, was negative 1, and so we end up with negative 9 as our answer. Okay, so it's about recognizing the limits and just using the graphs to get the values. All right, let's take a look. Composition. Again, be very careful about composition. Two-step process. Your first step, and like I said, and I usually write it above here, I need to figure out the limit as x goes to negative 3 of f of x, which I already did. Okay, right there. That is the new limit. The second step is to do the limit as x goes to negative 1 of the outside function. You decompose the function. Do the limit on the inside first, figure out where it went. Now we're going to do the limit on the outside function. So, and I'm going to use the graph to get it. I'm going to go up to g of x. I'm going to go to negative 1. And it's not continuous there, but that doesn't bother me. It has a limit. The limit is 1. So our answer to that is 1. All right, let's take a look at D. Again, two-step process. I'm going to come over here on the side. I'm going to decompose it, and I'm first going to do the limit as x goes to negative 1 of x squared, which is a nice continuous function I can plug in. Negative 1 squared is 1. So once I get that, that becomes the new limit, and I need to figure out where the outside function goes for that function value. So now I'm going to look at my graph and look as x approaches 1 on g of x. Both the limit and the function value are the same, and it's negative 1. So our answer here would be negative 1. Figure out where the inside goes, make that the new limit, figure out where the outside goes. That's your two-step process. Okay. Let's take a look at this one. We can do left limits or right limits using these same properties. So here I'm doing the limit as x approaches 1 from the left. The limit of a quotient is the quotient of the limits, provided the bottom is not going to be 0. And I have a scalar multiple on the top, so I'm just going to go ahead and kind of do a couple things in this step. I would do 2 limit as x approaches 1 from the left of f of x divided by the limit of a power function can just be done as the limit as x approaches 1 from the left of g of x, and then we square it. The fact that I have a left limit has no bearing on the properties. I can still use them. The only thing I'm still worried about here is I need this bottom limit to not be 0. If it is, I'm in trouble. So now I'm going to go up and get the limit as x approaches 1 on the left for g of x. So we'll jot it over here. Limit as x approaches 1 for the left. I'm going to need it for f of x, and I'm going to need the limit as x approaches 1 from the left on g of x. So I'm going to go up to my graphs and find those. On f, jump discontinuity, but I'm doing a left limit. I'm on the left side, and as I head toward x equal to 1, the y values are headed toward 2. So the left limit is 2. My right limit, or sorry, my left limit for g as x approaches, sorry, I just forgot where I was going, approaches 1. So here's my 1. Actually, the left limit and the right limit are the same there, and it's going to be negative 1. So we have negative 1. So those are the two things that I'm going to use in my properties. We go to do our problems. This part right here we know, right? The limit as x approaches 1 from the left, and this part we know. And we're just checking, because of the quotient rule, that we didn't get 0 in the bottom, and we don't. We end up with 2 times 2 over negative 1 squared, which is going to give me 4. And we have our answer. All right, one more problem. Let's take a look at this. A little bit more complicated. I have 5 minus a limit. All right, well, the 5 I'm just going to bring along with me. I'll come down here below. 5 minus the limit of a square root. I'm going to be okay. I'm going to start with the inside first. So I'm going to come over on the side. Okay, let's see, let's put it up here. I want to do the limit as x approaches -1. I'm just doing the inside right now because I need to make sure it's not 0. We have the limit of a product, x squared, so I'm going to go ahead and split it. Limit as x approaches -1 of 3 plus f of x plus f of x. All right. Just checking to see if I'd already done that one. I haven't. And then keep going. So we have the limit as x approaches -1 of x squared, direct substitution, that's 1. The limit as x approaches -1 of a sum is going to be the limit as x approaches -1 of a constant plus the limit as x approaches -1 of f of x. Okay. The limit of a constant is the constant, so that's 3, plus the limit as x goes to -1 of f of x, -1, oh, that's a d and e. d and e. However, do not say this limit does not exist. What you have to check, this is the thing where we've got some problems. We've got a discontinuity at x equal to -1. So we're going to have to start looking at some situations here. What we need to check now is we're going to have to do this problem in a two-step process. We're doing this, I'm going to break this up and I'm going to do a left limit and I'm going to do a right limit, and we're going to see what happens here. So I've already got the work here and we've gotten to this d and e. I'm going to erase that and I'm going to say, okay, let's think about this in two steps. Let's first look at the left limit. The left limit's not going to change the x squared part or the constant part. The left limit here, as x approaches -1, the left limit is 1. So we're going to put that in so we get 3 plus 1, which is going to, and let me change my left limit. I'm doing a left limit. I'm doing a left limit. We're going to end up with 3. Now we're going to look at the right limit, okay? Because we're doing this combination, it is possible to have the inside part not exist, but yet the combination end up being a limit that does exist, and we are going to check that. So now I'm going to do the right limit. The limit as x approaches -1 from the right of this x squared times 3 plus f of x. Now we've already done most of the work. You're essentially going to come down here and you're still going to have your 1, you're still going to have your 3, but now you're going to have the right limit. The right limit is 2. Alright, so that's going to give me my 5. These are not the same. So in this problem, the limit of the inside function does not exist. And if it doesn't exist because the left and the right aren't the same, we are done with this problem. We got a d and e, which would mean that we're going to end up with a d and e here. Okay? But you do have to check. We're going to do another activity later that we have to check left and right, and you'll see sometimes that ends up working. So the moral is that if you get d and e, don't stop. Look at a left limit, look at a right limit. You know that the limit of this big combination will exist as long as the left and the right limit are the same. And if it doesn't work out, then it doesn't work out. Okay? Because if you think about this, kind of why is this going to end up a d and e? I'll come back and just kind of show you both parts of it just to be thorough here. If I do this as a left limit, okay, here's my left limit. I got 3 on the inside. I would do the limit as x goes to 3 of square root of x, which is going to be 5 minus square root of 3. That's your left limit. Then what you're going to do is you're going to do your right limit. In your right limit, I'll come down here, you would have 5 minus, instead of going to 3, you're going to do the limit as x goes to 5 of square root of x, which is going to give me 5 minus square root of 5, not the same as what I got there. It's all about looking at left limit and right limit. All right? I'm going to stop this video here. That should be enough for our discussion next time.